started. All right, so we did last time where we discussed what the electric field and the charge and all of that's going to look like for different levels of spherical charges that are embedded with one another. So we've got this charge right here, this 2.5 microcoulomb at the center of a conducting sphere that has a net charge of 0, and it's got an inner radius equal to 60 centimeters and an outer radius equal to 90 meters. So I guess I need to draw that inner and outer radius respectively. So we'll call this R sub I and this one R sub O for the outer and inner radii respectively. And so if I want to know what the charge on the inner wall is, and specifically it says, what is the charge density on the inner wall? And don't forget that if you're asking for charge density, and since we're talking about an area, charge density sigma is going to be total charge divided by the area, which is why I dropped the area of the sphere in there, 4 pi r squared. So if I want to know what the surface charge density is on the inner wall of this outer shell, or of the shell here, how would I calculate the surface density here on this inner wall? Sigma sub I. Yes? Okay, so we've got a couple things going on here. I think Grayson's on the right track. We've got the charge here in the center, and this has no net charge. And so we talked about last time, what should be the charge on the inner wall right there? Yeah, the charge on the inner wall, Q sub I, is going to be equal to minus the charge at the center, which is going to be minus 2.5 microcoulombs. Good. Now, how did you reason that? Okay, so even if this did have some charge on it, let's say that maybe this had some charge Q equals 1 microcoulomb on it, your answer would still be correct. The charge on the inner wall would still be negative 2.5 microcoulombs. So why is it, at least in this configuration, always equal and opposite to the charge on the inside, Henry? Yes, so we said that inside of the conductor, the electric field right here, E, should be equal to 0 in that region. Okay, if the electric field is 0 there, we know from Gauss's law that you have to have 0 net charge inside of this radius right here. So inside of that green radius, we should have 0 net charge. To have 0 net charge, I have to have the charge here at the center is equal and opposite to the charge on the inner wall, which is how we came up with this statement. So if you want to know what sigma on the inner wall is, the charge density, I take minus Q over the area of the sphere, so that's 4 pi times the inner radius squared, so that's minus 2.5 times 10 to the minus 6 coulombs, all divided by 4 pi times 60 centimeters. Well, that's going to be 0.6 meters, and don't forget to square that. And that should give you an inner charge density of minus 0.55 microcoulomb per square meter. Or that would be negative 0.55 times 10 to the minus 6 coulomb per square meter. Okay, what about the charge density on the outer portion of the sphere? Well, an easy way to think about that is if instead I've got this radius that looks something like this, then what I get is I can just add up how much charge is on, or is in the center here, plus how much charge is on the shell. Well, how much charge is at the center is plus 0, so I get that the charge on the outer wall has to be equal to, is equal to Q. No, that's not the right way to reason that. Let's think about that instead. We've got the charge here drew in a charge of minus Q on this inner wall. And if this sphere has a net charge of 0, then if I've pulled in minus Q to this inner wall, then that has to leave a charge of plus Q on the outer wall here. So the outer wall has plus Q. It has the same charge as what's at the center of the sphere. The only reason that is because it started with 0 charge to begin with. Okay? So now, if I want to calculate what sigma is on the outer wall, then that would give me sigma equals, on the outer wall, is equal to the charge on the outer wall, which is just plus Q, divided by 4 pi r outer squared. And so you get 0.25 times 10 to the minus 6 coulombs per square meter, or that's 0.25 microcoulombs per square meter. Good. Any questions on that one? Remember, the electric field inside conductors in static equilibrium is 0. That will help you solve seemingly impossible problems to solve on a lot of occasions. William, you got a question? You would still, so even if the radius of the shell, the inner wall was 1 mile large, right? I mean, absolutely huge. Absent of anything else going on in the universe, it would still draw in minus 2.5 microcoulombs to the inner wall of the shell. The only difference is now you're dividing by a huge area. So your surface charge density would be very low. So you have the same charge spread out over a much larger area. Does that answer your question? Good. Any other questions? Yes, Henry.
So in the case that there was a charge on the conductor, would the field within it would still have to be 0?
The field in it still is 0 even if there's a charge on the conductor, yes. Sorry, I cut you off. Did I? That was it? Okay, yeah, even if there was a charge on the conductor already, then let's say that Q equals plus 1 microcoulomb or something like that. Or here's a good one. You've got, if the charge, let's say the charge on this, just for fun, was equal to minus 2.5 microcoulombs, right? So it's equal and opposite to the charge in the center. Well, we already said that we get that much charge as being pulled into the center already. So that would mean that the net charge on the outer wall here would be 0 in that case. Or if instead, if Q on the sphere was equal to plus 2.5 microcoulombs, we still get negative 2.5 microcoulombs right here, but we need a net charge on the shell. Well, that would mean that the charge on the outer wall, in this case, would be equal to plus 5 microcoulombs, such that the charge on the inner wall plus the charge on the outer wall comes out to be this net charge right here. But regardless, the electric field in static equilibrium inside a conductor is 0. Right, so the thing that we always want to consider is, at least for this shell as I've got it drawn, the total charge on this shell, right, is going to be equal to how much charge is on the inner wall plus how much charge is on the outer wall, right? And so in this case, let's start here, and then I'll go back to the minus 2.5 in just a second. Right now what I've got is 2.5 microcoulombs, should be the net charge, is equal to the charge on the inner wall. And because we're not varying this whatsoever, the charge on the inner wall, we said, was always minus 2.5 microcoulombs, right? Plus Q outer. So that's how, if I add 2.5 to both sides, that's how in this case I got the charge on the outer wall is 5 microcoulombs. But if instead I had changed this such that the charge Q is equal to minus 2.5 microcoulombs, right? Well, in that case, the only thing that changes here is the sign of this guy, right? And if I add this across, that's going to cancel those out. That gives me Q outer is going to be 0 in that case. All of the charge that was on the shell got drawn into the center to be attracted to the charge at the center. Yep. Okay. The next question asks us, find the electric field everywhere. And you're like, okay, great. Over the entire universe, how do I do that? Well, we can divide the universe into 3 distinct regions. The region inside of both walls of the conductor, the region in between the walls of the conductor, and the region outside of the conductor. We have each of those 3 regions. So what we want to do is find E, where E is going to be subject to R less than R inner less than R less than the outer wall, and then R outer less than R. We want to find it for each of those 3 regions. So how do we do that? Well, according to Gauss's law, let's take this first region right here. Actually, let's take the first one where we had right here. We already know that the electric field is 0 in between the walls of the conductor. So we only have 2 regions left to go. Ben? Okay, so his question was, can we treat the whole thing as a single point? We can do that for the last case, the bottom case, but not for the first case. Okay? Because if the shell has charge on it, and we shrink it down to a single point for the top case right here, we'll end up getting the wrong answer. And I'll show you why here in just a second. But if we think about this one right here, this region right here, where we're inside both shells, then what we have is that Gauss's law states is that the flux, or E, dotted into an area that we integrate over, is equal to how much charge is enclosed by that area divided by epsilon naught. Right? And due to symmetry, since this is a uniform charge, like there's no distribution to that charge, we end up getting that's E times 4 pi r squared equals Q enclosed. Well, that's just going to be little q, as we called it, divided by epsilon naught. Or in this case, that's going to be Q over 4 pi epsilon naught times r squared. Go figure. Using Gauss's law, we recover again what we said Coulomb's law was going to be, or what we said already back 2 weeks ago, what Coulomb's law is. So the two match one another. Because, as we stated last time, K is equal to 1 divided by 4 pi epsilon naught. So we have KQ over R squared for the electric field. Well, what about the electric field outside the shell and the charge in this outermost region right here, where now we're looking at, instead of this region, we're looking at this outermost region right here. What is the electric field in that outermost region? Or at least what is the form of that electric field in that outermost region? Because it's a sphere, we still have, it's going to be something divided by 4 pi epsilon naught r squared. And that something that we're dividing is going to be how much charge is enclosed. Right? How much charge is enclosed? So, in this case, the charge that's enclosed, Q enclosed, is equal to the charge at the center plus the charge on the shell. But the charge on the shell is 0. So we still have the same amount of charge enclosed by this outermost green circle here. So we still get that it's Q over 4 pi epsilon naught r squared. The form of the electric field in both regions is the exact same because there is 0 net charge on the shell. The only thing that changes is I'm dividing by a bigger radius. So the electric field drops off as 1 over r squared. Okay? Any questions on this one before we move on? Yeah. Yeah, if it only has a net charge of 0. What if instead it was this case right here where the conductor had a net charge equal and opposite to the charge in the center? What would the electric field outside of the conductor be? 0, yes. Yeah, because the charges cancel out, right? If I add up all of the charge here, I'd have plus 2.5 microcoulombs minus 2.5 microcoulombs. That comes out to be 0 net charge. And so that would go away. Okay, that would go away to 0 right here, right? Or if instead, if this had a charge of, since this is what we've been doing, if this had a charge of Q equals plus 2.5 microcoulombs, well, in that case, I'd have Q is 2.5 plus big Q is 2.5. So that would be a total of 5 microcoulombs on the top, right? So we're adding the contributions of charge from the point charge at the center and the shell after it. And you could go through and do it layer by layer, but you'd still get the same result, right? Like if you took it as the charge at the center plus the charge on the inner wall plus the charge on the outer wall, you'd still come out with the same result if you've done Gauss's law right iteratively. Yeah, good question. So in this case, what ends up happening is on the outermost wall, you end up having the total net charge represented on the outermost wall. Yes, and that's true no matter how many layers of shells that you have too. Good question. Makes me think of Emperor's New Groove, right? When he's giving the birthday gift to himself and he says, I'm so happy. That just makes me happy when things like that click in class. Emperor's New Groove, underrated Disney movie. Any other questions? All right. So with this one, what we end up getting is that whether you go back and calculate when we did the electric field above infinite planes of uniform charge, right? We did that back a few class periods ago. Or you could do it with Gauss's law, and you get the same result. And that result, if you don't have it written down, is that over an infinite plane of charge, the electric field comes out to be equal to sigma over 2 epsilon naught. And so the problem is we have to consider in this one that the electric field is going to be a function of vectors, right? At least for the first one, sigma 1 is going to be going up. This lies in the xz plane, and so n1 hat is going to be equal to j hat, right? And I think in this one, let's just look here at this case where you've got x and y. Let's forget about this case for just a second. So if we're looking at this, you can go through and convince yourself that x of 6 meters and y of 2 meters is going to lie between the planes. And so we also need to consider what the normal direction is here based off this plane. So let's call this n2 hat. And how do we figure out what n2 hat is going to be? Well, hopefully I can convince you that if as the top plate starts rotating away with some angle theta, right? Well, then let's consider the case where theta is 0 degrees, where this right here being theta is 0 degrees. Well, in that case, n2 hat would just be pointed in the minus j direction, right? But then, that's if theta equals 0 degrees. And then if theta goes to 90 degrees, then in what direction is n2 hat? What? The positive x direction. It comes out to be plus I hat. Yes, that's correct. So we need to have something here that's going to, if you will, oscillate between I and j, right? And so what you end up getting is that n2 hat is equal to 0. It's going to be minus j. So minus j cosine theta plus I hat sine theta. Or specifically, when it's equal to 30 degrees, that's going to be minus j cosine 30 degrees plus I hat sine 30 degrees. You could think of it this way instead if we project it onto, if that's a little non-intuitive to you, is if this is the x, y plane here, and this plane of charge is going to lie something like this, where this is that 30 degrees, and then this is n2 hat like so, right? then I want to draw this out such that this angle right here is also 30 degrees. And now you can find the x and y components of that. So I want to find the y component of it and the x component of it. And that will give you this same result right here. Okay? Any questions on how I at least calculated what N1 and N2 hat are? William? Yeah. So that was actually going to be one of my follow-up questions. Why did I assume that N2 hat was facing down towards the other one and not up away from the other one? How did I? Well, first of all, I know that for the bottom plane, the reason that I chose the upward-facing vector instead of the downward-facing vector is it said I'm at x equals 6 meters, so that's somewhere out here, and then y equals 2 meters, that's going to be, y equals 2 meters, that's going to be above the plane right here. So that's why I chose that one. But how did I know that I need to choose the downward-facing vector for part A instead of an upward, up to the left-facing vector from the second plane in part A? How would I go about calculating that? Yes, I do know my positions below that plane, but how do I affirm that that position, 6-2, is below the angled plane? How do I confirm that? Yes, you could use the tangent. Let's take here that we've gone out to x equals 6 meters, right? So we've got this point right here. And we want to determine if this 2 meters here looks like this. So I've got this right here. Or if it looks like this. We don't know if we're above or below the plane yet. So how do we determine whether we're above or below the plane? Well, remember, if I want to know specifically what this position is, how would I calculate that? If I know what x is. Well, we've got that the tangent of theta, if this is theta right here, is equal to y over x. Or y is equal to x times the tangent of theta, or y is equal to 6 times the tangent of 30 degrees. Right? And what do you get for 6 times the tangent of 30 degrees? I don't have it written down on my notes over here. .46. So if I know I'm at x equals 6, then that only leaves me the case where in this, as far as what I'm concerned here, that I'm below, 2 is less than 3.46, so I'm below the angled plane. So that's how I chose the normal vector that was down and to the right instead of the corresponding one that's up and to the left. Does that answer your question? Okay, good question. So if I want to know the electric field inside this region, then I have to consider that there is some electric field from this plane that's going to be going down and to the right. And then I've got additional electric field going from the bottom plane that's going to go up sort of like this. And if I want to know the net effect is equal to the electric field from 1 plus the electric field from 2, Or in this case, that's going to be sigma 1 over 2 epsilon naught times j hat plus sigma 2 divided by 2 epsilon naught times I hat sine 30 degrees minus j hat cosine 30 degrees. And sigma 1 and sigma 2 are represented up here. That's how I knew, by the way, that the normal vectors should point, or the electric field should point away from each one of these sheets. If one of those had been negatively charged, I would have had to throw in that negative somewhere in the mix, and it would have flipped all of our electric fields over by the matter that there would have been a negative sign tucked into one of these two terms right here, or both. But at least as far as what's given here and how we've derived it, this would work. This solution would work whether it's positive or negative charge, just so long as you put that positive or negative charge in the right place on sigma 1 and sigma 2. And now we know epsilon naught, if you don't have that written down, epsilon naught is equal to 8.85 times 10 to the minus 12, and I think that's in farads per meter. So if we convert this to coulombs per meter squared, so multiplying by a factor of 10 to the minus 9, what you end up getting when you add all of this together, remembering that we can only add j components to j components, or I components to I components, but there's no I component in the first term, what you end up getting is 1.27 times 10 to the 3 coulombs, Newton per coulomb in I hat plus 1.47 times 10 to the 3 newtons per coulomb j hat. So because the surface charge density on the bottom plate, not the angled plate, is greater than the surface charge density on the top plate, we get that it dominates here, and it's going to cancel out the downward effect of the electric field from this angled plate right here. Remember, as you move away from point charges, the electric field strength drops off as 1 over r squared. But as you move away from a uniformly charged sheet, the electric field does not drop off. It stays the same strength everywhere in space. So at that point, it's just a matter of which plate is stronger, not whether you're closer to one plate or the other. Any questions on this one? They were given to us. Sigma 1 and Sigma 2 were given in the problem. They were 65 and 45 nanocoulombs per square meter. Yeah, right up here by the mouse. So now, if you were to do Part B, what would change? What would change in Part B? Yeah, you're above the second plane. So in that case, this vector is going to rotate by 180 degrees. Or when we flip a vector over, then the only thing that changes in that case is that N2 is going to be equal to plus j cosine 30 degrees minus I hat sine 30 degrees. So basically, you'd throw a negative sign right here instead, and you would end up with a new solution. It's very similar to the first one, and you can see that on my published solutions on Canvas. Good. Now, if you really want to have fun with this, you take electromagnetic theory, and instead of having uniform charge density, you have uniform electric potential electrical engineers. You hold one at +1 volts and one at -1 volts, or grounded, whatever you prefer, but you hold them at two different potentials, assuming there's some sort of gap between the plates, so that way it doesn't short out. And at uniform potential instead of uniform voltage, the charge collects down there at the sharp point. The charge density decreases the further away you get from the intersection of those two plates. It's just a fun little exercise using partial differential equations and all that fun stuff. Any questions? All right. Let's hop to. Whew. Anybody up for learning an additional language? As if math wasn't already an additional language enough? I've always said that math is my first language, English is my second language. So it's no wonder I did so poorly at reading and grammar and all that kind of stuff, because I was an ESL student. Do what? Apparently that's not uncommon in the world of engineering and science. You know, we've got people who are more mathematically minded than they are anything else, so it's fun. There was a competition a few years ago. I want to say I don't remember what school it was, but it was a competition to see who could come up with the biggest number ever, the largest number, and the only rule was you weren't allowed to use the same form of a number twice. So if you used an exponential, you could never, the next person couldn't use an exponential again. And the winning solution was pretty much a sentence written with set theory notation, where it said that the number I choose is always one greater than the number that anyone else can choose. And it was like, wow, that's beautiful, that's awesome. So if you want to have fun, go look up that video. Okay, or don't, because your physics professor is a nerd and you're not that nerdy. Let's talk about electric potential. In circuits, it's all about your potential connections. Ha ha ha, good pun. Thank you, I appreciate that. So electric potential. The question that we have to consider before we can even talk about electric potential is, you all took Phys 1. We're going to build this whole discourse on electric potential based off of potential energy, right? So someone tell me really quickly, how would you describe how an object moves subject to something from last semester, gravitational potential energy, right? You've got the Earth is in an elliptical orbit around the sun, or take one that's even more elliptically inclined, like a comet. So something that has very high eccentricity. Describe to me the motion of that comet using only energy considerations. Yeah, so we said that gravitational potential energy, when is a factor of 1 over r, right? So as you get further and further away, your gravitational potential energy drops off in magnitude, but you are actually storing gravitational potential energy because there's a negative out front, right? And so as you think about this, let's think about after the comet has already done its slingshot around the sun. So it's going further and further and further away from the sun. It's gaining or raising its potential energy, and that energy has to come from somewhere. So it's coming from the kinetic energy term. It's losing speed, it's losing kinetic energy, storing that in gravitational potential energy, until that tangential velocity is enough that you get zero radial velocity, and it turns around and starts, the better way to think about it is falling back towards the sun, right? So it falls back towards the sun, it decreases its potential energy. That decrease in potential energy has to go somewhere, so it goes into raising the kinetic energy. It goes faster and faster and faster, and on and on and on. The cycle continues of going slow and slow and slow further away, and then falling faster and faster and faster going towards it. It turns out that we wrote that down as being a differential change in potential energy is going to be equal to minus the force times a differential change in length. And we could have broken that up into x and y and z components. And you can rearrange this equation using an operator that you have likely never seen before, but I want you to be aware of, but we also won't use all that much in this class because we're going to stick to one dimension. What I want you to remember is that we said that for a force that is conservative, meaning that we can associate a potential energy to that force, if you want to know what the force is at any position in the x direction, then that's going to be equal to the negative derivative of the potential with respect to the position. This upside down triangle with a vector sign over the top of it, its name is affectionately known as nabla. So that's a nabla, that upside down triangle is nabla. And the way that you would read that is what's called the gradient of the potential energy is equal to the force, or the negative gradient of the potential. The only thing that that fancy upside down triangle does is say, okay, if we're talking about a change in the x direction, we have to take the derivative with respect to the x direction, and that change also points in the x direction. In the y direction, you take the derivative with respect to y, and it points in the y direction, j hat. In z, take the derivative with respect to z and point it in k hat. That's all this does, is you have a sum that ends up looking like this term up above right here. But I want you to mostly be concerned with our one-dimensional cases where the force in the x direction is equal to minus du dx. Or in this case, the force in the r direction, is going to be du dr for the picture there on the right. And that picture there on the right, by the way, comes from your textbook, chapter 8 or something like that, the chapter on gravity. So if you want to have a bit of a refresher on this, with something that you're at least a little bit more familiar with, take a look at that chapter again. Knowing that the force is equal to the negative derivative with respect to the position, we note that objects want to move down in potential energy curves, right? An object is seeking to decrease stored potential energy, and it wants to move inward along this curve, increasing its kinetic energy as it goes. I had a great Desmos demonstration on this that I built last semester, and over Christmas my account got corrupted and I lost all my great demonstrations. But it looked really cool, and you can trust me on the fact that it looked really cool, and we'll just move on with our lives. But we want to decrease potential energy. And the reason that I'm recalling all of this stuff is I know not all of you are students like I was growing up, and you didn't brain dump all of Physics 1 as soon as you took the final exam. I did that. I'm hoping you didn't do that. But if you did, it's just a little bit of a reminder that, hey, the things you learned in Physics 1, Physics 2 builds upon that. So we use that because electric charges behave in the same way. Beginning with the simple fact that for a conservative force, a change in potential energy is going to be equal to minus the force dotted into a infinitesimally small change in its position, which is what dl is. And we said that electric force is equal to a charge times an electric field. Then in this case, we get du is equal to minus q times E dot dl. And so what we want to define is if we divide by the charge everywhere, then we get a differential change in this thing that we're going to call V. So that's potential energy divided by a charge to experience that potential energy. Or that's equal to minus E dot dl. So this differential change in this new variable V is just a negative, the negative of an electric field dotted into some infinitesimally small step along that electric field. And this new parameter V we're going to call electric potential. And if you get nothing else from today's class, what I want you to hear is that when we're talking about electric potential, when electrical engineers, when you're talking about electric potential, voltage, you are implicitly talking about, when you stick charge into that region, the potential energy that the charge will have in that region and its change in potential energy. Meaning, what motion is going to occur when you have a potential that exists? Well, inside of a copper wire, you're going to have the current is going to go from high potential to low potential. We'll talk about why here in just a second. So, electric potential between 2 points A and B, say this is point A and this is point B. A is where the hollowed out circle is. B is where the charge exists now. It's just the difference in potential at these 2 points. And that's equal to minus the integral from A to B of E dot dl. This is measured in volts, which is just a joule energy divided by charge, a coulomb. And taking the derivative of both sides, or dividing by dl on both sides, then I get dV dl is proportional to the electric field strength. And the reason that I point that out is we said before that electric field strength is measured as newtons per coulomb. But by this logic, newtons per coulomb is the same as taking volts per meter. So we can measure electric field strength in newtons per coulomb or volts per meter, and we're measuring the same thing. And just like electric potential energy, gravitational potential energy, spring potential energy, we don't care what the electric potential is at any given point. Right? We don't care what the electric potential energy is at any given point. What do we care about when we talk about potential energy? The beginning and the end. How does it change? Right? And so if we care about how electric potential energy changes, is the electric potential energy higher here and lower here, then we're saying the same thing when we're talking about electric potential. How does that electric potential change? Right? So electrical engineers, you take a look at voltage across a resistor. And you measure the voltage on one side of the resistor is 10 volts, and the voltage on the other side of the resistor is 9 volts. You have had a decrease of 1 volt. Well, What happens if you have a measurement of 20 volts on one side and 19 volts on the other side? Well, it's still dropped by 1 volt. You still have the same change in voltage. You still have the same current. We'll talk about that in a few weeks with Ohm's law. You have the same parameters so long as you have the same drop in potential across that resistor, right? So what changed when I said that on the first side of the resistor you had 10 volts and then you had 20 volts, but the voltage difference across them was 1 volt or negative 1 volt? The only thing that changed was your reference point changed, right? So V reference, your ground, changed. That's all it was. We only care about how electric potential changes. Sorry, I don't know why the text ended up so small on this slide. I'll try to fix that. Since dV is equal to a change in electric potential is equal to change in electric potential energy divided by charge, you can multiply by charge on both sides. And if you take a charge and multiply it by a change in electric potential, you implicitly have a change in electric potential energy, right? You take a proton and you move it through a 1 volt difference, then there has to be a change in potential energy that had to occur. I take a proton, I started at 10 volts, it then moves to a region of potential 9 volts, so it's gone down in electric potential energy. Then I have to be talking about how much energy, potential energy it changed. From that, we can implicitly talk about how much the kinetic energy changed because the potential energy changed. And in this case, it's supposed to be imagine. Imagine the energy change of an electron with charge Q equals the elementary charge accelerated through a potential of 1 volt. The energy change is the 1.602 times 10 to the minus 19 coulombs times 1 volt, or that's 1.602 times 10 to the minus coulomb volts is equal to 1 eV. And what I should have out there too, a coulomb volt is the unit of energy, a joule. So if you ever hear it tossed around that it's a 10 MeV particle, 10 MeV mega electron volts, well, in that case, you have to consider that this would be your conversion right here to go from electron volts back to joules. So think about how much energy is stored in that particle in terms of a macro scale quantity that we tend to think of. But it's off by a factor of the elementary charge. Okay. So we said that the equation is delta V is equal to minus E dot dL. Therefore, electric field lines go from high potential. You can see that in the image here. Electric field lines start at high potential and go towards low potential. Just like we said that electric field lines have to originate on positive charge and terminate on negative charge, we've got the same thing here. One of the things that we did at Harding, an experiment that we would do, is we would take silver paint on a slightly conductive sheet of paper, and you would draw a straight line and a straight line, mimicking a parallel plate capacitor is what we were doing. And you'd set one plate at 10 volts and one plate at 0 volts. You'd ground the other plate. And the first question that we asked was, the plate that was set to 10 volts, positive, negative, or neutral charge? Which one is it? 10 volts, positive, negative, what? it's going to end up being positively charged because the voltage is positive. We want, again, if this was at 10 volts right here, we would need it to be positive for the electric field lines to start there. So higher potential, we got positive charge. But then you look over here at the right-hand side at the grounded plate, so 0 volts. The charge of that right plate at 0 volts is positive, negative, or neutral. Which one is it? This one, even though the potential is 0, you still get that it's negatively charged, right? Because we need that all of these electric field lines to terminate over here at this 0 volt plate for them to be straight lines as such. We'll get to this here in a second, but I'm just trying to preemptively give you some mental pictures here to give us that this grounded plate, because it's at lower potential, has all the negative charge on it. The electric field E points in the direction which the potential V decreases most rapidly. So, why I say that is, if you imagine your electric potential in some region, if you've ever seen a contour map by the USGS of the planet, right? A contour map looks something like it's got all those different lines on it that tell you, okay, as you go this direction, you're going up in elevation. As you go this way, you go down in elevation. Well, if you can imagine electric potential looks something very similar, where you can now draw it as contours, or we'd call that the contours, we call those equipotentials. Everywhere along this contour is equal to 5 volts, let's say. And you draw that contour map out, then the direction that it changes most rapidly in the negative direction is going to be the direction of the electric field. And no, this is a lot to throw at you. I'll show you that same FET demonstration here in just a second, where we had the charges in the electric field, but we're going to drop electric potential onto that grid as well. So if I release a charge in an electric field, we release the positive charge particle in the figure to the right. Recall that the electric field lines begin at positive charge, end at negative charge. Therefore, positive charge corresponds to higher potential than negative charge. This is what I was trying to talk about with that experiment that we would do at Harding in the lab. So this high potential region has to be positively charged. This low potential region has to be more negatively charged. And the reason that I state it that way is we can describe what happens when we release this charge in terms of the forces, in terms of the electric field, in terms of the electric potential energy, or in terms of the electric potential, and we all are making the same statement. Whether I say it moves to the right because it's moving along the electric field lines, right? A positive charge follows electric field lines. Therefore, it moves to the right. Or I could say that the positive charge is repelled by the positive charge here on the left-hand side, and it is attracted to the negative charge on the right-hand side. Same statement. Or I could say that it's moving in the direction where it decreases its potential energy, right? When you release any object, it spontaneously wants to move in the direction that releases or decreases potential energy. Or I could say that in this case, the electric potential energy decreases. All of those statements, those 5 statements, are equivalent statements. The first one I'm talking kinematically, the second one I'm talking in terms of electric field, the third one in terms of Coulomb force, the fourth one in terms of how things respond to spontaneous changes in energy, and the fifth one in terms of how charges respond to electric potentials. Correspondingly, if I release a negative charge in this region, so imagine at the mouse now, instead of a positive charge, that's a negative charge. Well, it's going to want to move to the left. And the reason it wants to move to the left is because it follows the electric field lines opposite the direction that they're pointed, or because they're attracted to the positive charge on the left and repelled by the negative charge on the right, or because it's trying to decrease its potential energy, but to decrease its potential energy, it has to increase its electric potential because it's a negative charge. These are 5 equivalent statements. I think last year on the final exam, I did a choose all that are correct kind of option, and I basically put one of these 2 slides on there, and I said, which one of these statements is correct regarding the motion of the particle when I release it? All 5 statements were correct. My point was, these are all equivalent statements. Good. You asked the question that was on everyone's mind. Why does the electric potential energy decrease while the electric potential increases? Well, recall that what we stated was, or how we defined electric potential, was equal to potential energy, and maybe we should say more specifically, a change in each one of those is the same with respect to the charge that's present, right? And we can then say that, okay, Q times delta V is equal to delta U, right? Either one of those are the same. But we know that spontaneously, this is always going to decrease. Right? That the change is going to decrease. Or we would say that that's negative. Right? But for a negative charge, I've got that right there. So a negative divided by a negative charge means that this over here is going to end up being positive, meaning that negative charges will increase potential spontaneously. Does that answer your question? Yep. I'll go ahead and tell you, I tend to do this every year, even though I don't mean to, because I tell everyone that I always do this, but people still make the same mistake. Usually on the exam, I'll have one of 2 pairs of questions. The first pair of questions is, based on this configuration of charge, what's the electric force on this other charge? And then as an immediate follow-up question, I'll say, what is the electric field at this additional charge? And inevitably, when I look at people's scratch work, they do the calculation twice, right? They go through the whole procedure of adding up all of these vectors in terms of the force from this one plus the force of this one plus the force of this one equals the net force. And then when I ask about the electric field at that point, they say the electric field due to this one, the electric field due to this one, and the electric field due to this one. And they do the problem twice, when all I'm trying to see if they remember is, hey, by the way, did you remember that a force is equal to a charge times an electric field? So yeah, the first one might be a lot of work, but then for the second one, you just divide by the charge that's present at that point, and it gives you the electric field. Right? That is, if in the second one I ask you what E is, don't go through the rigmarole of saying, okay, Well, this one was the sum of k q sub I over r squared times r hat. And then this one, man, I got to go through it again and say that it's the sum of k, oh, and that was times q, sorry. This one is k q sub I over r squared r hat. Well, instead, just take the force that you calculated in the first one and divide by the charge. Boom. Roasted. Michael Scott. Same thing. The second type of question that I usually pair together is calculate the change in potential energy of a charge moving from here to here in this configuration of charges. And then I say, calculate its change in electric potential. And inevitably, students calculate it twice, when all that I'm asking for is divide by or multiply by the charge between them. Don't do extra work. Remember the relationship between each of these things. In fact, we'll draw out a concept map if we've got time by the end of all of this. Okay. Electric potential can increase while potential energy decreases. True or false? Andrew. We're assuming the field is the one generated externally of the charge that's present inside of the field, yes. So it doesn't change. I'm sorry, I don't state your question again. Yep, negative that, but yes. Minus E dot dl. Yep.
So then the sign would be determined on which over DL. DL is the determining factor in the sign.
Yes, yes. So this is a true statement, by the way. These two things you can increase. But going to Andrew's question, let's say that my electric field looks something like this right here, right? But L looks something like this, right? So this is L right here. This is the path that I'm walking through that field. Then what you have to consider is we said that delta V, let's call this point B and this point A, is equal to minus the integral from A to B of E dot dl, right? So what you have to consider is, let's take dl at this point right here. And dl, the differential step change, is always going to be tangent here. So this is dl. Whereas our electric field is pointing to the right in this case, right? So what you end up getting is E dot dl is equal to E cosine theta dl, where theta is that right there, right? Does that answer your question? So we're only concerned about, you think about, okay, what about this case right here where they're almost perpendicular to one another? Well, if they're perpendicular to one another, the cosine of 90 degrees is 0. So that means that while I'm perpendicular to these electric field lines, this could all be 10 volts. This could all be 9 volts. These are all equipotentials. That as I move along this line, I'm not changing my electric potential, because the angle between them, between where I'm walking, this blue line here, and the direction that the electric field is pointing is 90 degrees. Cosine of 90 degrees is 0. And so what we're going to see here in a second is, let's call these different equipotentials, right? Well, what you end up getting is that the electric field is always going to be perpendicular to electric equipotential lines. So something like this right here, for the case that I've got drawn. This would have to be what you end up getting for the arbitrary case I drew up there. So equipotential lines, the contours of my electric potential are always perpendicular to the electric field by convention. It's actually what that upside down triangle, that's the nature of how that operator works, the gradient works. Does that answer your question? Okay. Good. Note that our equations for electric potential are with respect to changes in electric potential. Therefore, like in problems dealing with potential energy, it's convenient to choose a reference point, some good reference point where V goes to 0. It turns out for point charges, the most convenient place is R equals infinity. Because the electric potential is going to go as 1 over R, we'll see in a second. And so setting it to be 0 is going to match where the asymptote levels off as well. So, according to my friend Smeagol, tricksy question here, an object can be accelerated, that is to say, experience a force when V equals 0, true or false? Good. An object can be accelerated when V is 0. The only thing that we need is when V is 0 is for it to have non-zero slope, right? If it's non-zero slope, because the force is the derivative of the potential, then what we're asking about is the slope non-zero even if the potential is 0? So, we derive the electric potential of a point charge from the fact that the electric field is kq over r squared. Therefore, V at some point, call it this point here on the image, on the top right of the image, is equal to V at that point minus our reference, which we'll say is 0, is going to be kq over r squared dr. And if this is going to be our V reference equals 0, that happens at infinity. So, electric potential is equal to kq over r. And if you want to know the electric potential energy stored between two charges, just multiply by the magnitude of the second charge. U is equal to k q1, q2 over r squared. Not a lot of time for our PhET demonstration here. The main takeaway here is that bottom line, potential for a point charge is kq over r. And like I was saying, if you want to know the potential energy is going to be kq of the first charge times q of the second charge over r. That would be the potential energy stored between two charges in proximity to one another. And just like we did with electric fields, you can add up the net potential in any region due to point charges is going to be the sum of the individual potentials. But in this case, potential energy and electric potential are not vectors. So, the classic example, I'll bring this slide back up because I know you're writing furiously. You've got a plus charge and a plus charge, and we go to the midpoint between them. Right? Well, due to symmetry, we've got as much electric field pointing to the right from the left charge and pointing to the left from the right charge. The electric field at this point we expect to be 0. But what we don't expect due to this is that V in this case is going to be non-zero. Basically what ends up happening is you get a sort of saddle point between these two on your contour map. Right? Between them, you'd expect the electric potential to be, if I could draw here, let's call this X, and let's call this V, then what you expect is that the electric potential is going to look something like this right here. Why did that go away? Why did it think I was trying to erase that? I don't know. So, V is non-zero here, but the derivative of V with respect to X is 0 at that point, meaning that E is 0. Okay? If one of those charges was negative, then you would end up getting that the potential at the midpoint is 0, but the electric field is non-zero. Just an interesting exercise to try. The net potential is going to be the sum of the individual potentials due to a system of point charges. And you can see that if you want to click this on your own device. I know we've only got 3 minutes left, or if you want to just follow along on the screen, that link just takes you right back to the same thing that we had before, where I could drop, say, a positive charge right here and a positive charge right here, and I get my sensor at this point is going to give me at the midpoint an electric field that's pretty much 0. But the thing that I didn't do before was you can also turn on the potential in the background there, the little faded region, and you can grab this little sensor and you can say, okay, at this point right here, I'm going to drop this and draw a line. That little green line that popped up is an equipotential, where the potential there is 30.4 volts. And then I could drop one right here, and I get that is going to be 19.9 volts. And then I could have 10 volts is going to not exist in here, so let's drop one at 15 volts. You could drop one here at 25 volts just to get an idea. And then you could also drop one here at 15 volts. And you could do the same on the other side. And if I look at electric field, you can see that the electric field, which is the big red arrow, is always going to be perpendicular to those green lines. And you can play around with this. You could even drop this charge back in and do this for a negative charge instead. And you could get a potential of 0 here at the center, but an electric field that is very clearly non-zero at the midpoint between them. But do this for any configuration of charge. Draw problems that you're assigned on your homework out in this, not to get the answer because the scales are different, but at least to get an intuition of what the answer should be. Guys, we still have a minute left. Come on. Y'all go ahead. Y'all have a great day.